Hello everyone and welcome back to another video. Today we're going to be taking a look at Euclid 2025, question 6b. In the diagram, quadrilateral ABCDA has ABC equals CDA equals 90, AB is 56, BC is 33, CD is 39, and DA is 52. Point P is on AD so that BP is perpendicular to AD. Now we should determine the exact length of BP, which is going to be this altitude right there. So for this question, I found two solutions. First one is the more common solution. Oh, I don't want to save it. First one is the more common solution, and a solution that I think is actually better and more efficient. Second solution is kind of a fake solution, but it does solve the problem. It just uses three formulas to solve it, just formula crunching. But to do that, you'd have to know the formulas, and there two of them you might know, the other one not so much because it doesn't come up in a lot of contests, but in AMC you might want to know these three, all three of them. So that's why I'm just showing that second one. But yeah, let's get started. So the first solution requires some trig knowledge, trigonometry knowledge. So this is the trig solution. So we're going to be using the right angle at B and the right angle at D to form two right triangles. We can do that by joining AC. Like that. And by doing that, we actually create these two right triangles, ABC and CDA. And using Pythagorean theorem, we can find the length of AC, right? Because they actually both share this hypotenuse. So we can quickly apply Pythagorean theorem. We can do it with AD and DC. So 52 squared plus 39 squared is going to get us AC squared. And then we get that AC is a nice integer value, 65. Now we know all three side lengths of both triangles that we've constructed, right? And because we know all three side lengths, the question becomes very easy because we can just apply right triangles, trigonometry on right triangles. So let's let this be theta and this be alpha because we can solve for those angles. Remember that we don't want to be approximating the values though of theta and alpha because the idea is to find BP and we cannot approximate BP because the University of Waterloo contests look for exact solutions, exact answers, whether that be in radical form or fractional form, but they're not looking for decimals that approximate values. So we're going to have to not approximate, but add them in a clean way to eventually get this entire angle, which then we will use this hypotenuse 56, the angle, to get BP. So yeah, I kind of mapped out the solution there, but let's get into it. So we know this is theta, so let's create some equations. Let's use blue. So cos theta is going to be 56 over 65. If you don't know where that comes from, there are two ways to know it. There's the conceptual understanding and SOHCAHTOA. You might have heard of SOHCAHTOA. This is just the mnemonic device we use to memorize all the ratios in trig for right triangles. But obviously it's not the best way to understand trig. Cos theta equals 56. And we have that sine theta is 33 over 65. And for alpha, cos, let's do it a bit higher. Cos alpha is 52 over 65. And sine alpha is 39 over 65. So we got all four of the equations we could get from trig, and obviously this will be 90 minus alpha, this will be 90 minus theta. but we don't need to worry about that because we're only looking for the sum of these two angles, right? What is the sum of these two angles? Well, we have a formula for that. Sine theta plus alpha. Why are we looking for sine? Looking for the y value. If we were looking for cos, we'd be looking for this value, and that's going to be kind of useless. And it will take a lot more time to solve for the y, right? But we're looking for BP. So we look for the sine of theta plus alpha. And we scale it up by 56, because that's our hypotenuse. And that's going to be equal to BP. Now, what is sine theta plus alpha? That's going to be sine theta cos alpha plus sine alpha cos theta. I don't know why I use square brackets there. Maybe I thought it'd be like that. I don't know. Equals BP. And yeah, we can sub in that sine theta is 33 over 65. Cos alpha is 52 over 65. And so on and so forth. So let's go ahead and do that. Let's change it back to the normal brackets. And we know that the denominator is going to be 65 squared, right? Because we're multiplying 65 times 65 in the denominator. So we can just leave the denominator to be 65 squared. And then we have some number crunching to do. But sine theta is going to be 33 times cos alpha 52 plus sine alpha going to be 39 and 56. And you can punch this into your calculator. You'll get 672 over 13 equals BP. If it's AMC and you don't have a calculator by your side, then you can do some canceling. 65 squared is actually just 5 squared times 13 squared, right? We prime factor it. There's a 13 here, so that becomes a 3. Let's do a different color. This becomes a 3. This becomes a 4 because it's also divisible by 13. And yeah, arithmetic does become easier though, because we get 33 times 4 is 132, and 3 times 56 is 168. And yeah, that's all going to be over 25 times 13, or 56 obviously. And this is actually becomes 300, right? 300 over 25 is 12. 12 over 13 times 56, 672 over 13. So yeah, that's our answer. Now let's go to the formula crunching solution, because I think you guys should know these formulas as well. And now for the formula crunching solution. So we're going to use Pythagorean theorem, obviously, to get this length here. Do it in a different color. $65. And now we're going to use Ptolemy's theorem. So it says that in a cyclic quadrilateral, the sum of the products of the opposite sides is equal to the product of the diagonals, right? Is this a cyclic quadrilateral though? How do we know it's a cyclic quadrilateral? Because the opposite angles add up to 180. And if they do add up to 180, that's a property of cyclic quadrilaterals. This quadrilateral can be inscribed in a perfect circle. So that means that all the vertices touch a point on the circle perfectly, right? Nothing is inside or outside, but they touch on the circles. So because we know that this is a cyclic quadrilateral, we can actually use Ptolemy's theorem. So sum of the product of the opposite sides, 56 times 39 plus 33 times 52 equals the product of the diagonals, 65 times this diagonal, which is going to be BED. And then we get that BD is 60. Because it's pretty easy to solve. We only have one unknown and one equation, so we're good. Now that we know that that's 60, what do we do from here? Let's introduce another formula, Heron's formula. And it says that, let's say let S be the semiperimeter of the triangle. Semiperimeter is just the sum of the side lengths of the triangle divided by 2. So that's going to be, in this case, 84. In this case. And it's this big thing. The area is going to be equal to 84 semiperimeter times, I'll do generalized, S times S minus A, S minus B, S minus C. A, B, and C are the side lengths of the triangle. So S minus the first side length, S minus the second side length, and S minus the third side length. And that is going to be the area of the triangle, actually. So, pretty useful to know for AMC questions. This is the first time I'm seeing it come up in a Waterloo contest. But I guess, miracles happen. So let's quickly crunch those numbers. Okay, let's go. So, we know that the area is also going to be 52 times BP, right? That's why we're doing Heron's formula. So 52, let's call it H, I guess. It's the height of the triangle divided by 2, is our Heron's formula. So 84 times 84 minus 56 is 28, times 84 minus 52 is 32, and 84 minus 60 is 24. So that comes to 26, so 26H, and this actually comes out to an integer value, 1344. H is 1344 over 26, which becomes 672 over 13, and we're good to go. So that is the crunching of 1, 2, and I guess Pythagorean theorem, however you spell that, I think I forgot. But yeah, 3 formulas we use to solve this problem. So if you know them, you know them. If you don't know them, you don't know them. I mean, if you don't know them, just use trig, right? Because trig is the better way to solve this question. But yeah, so that is that. Thanks for watching.